Welcome to the webinar on motor control with Embedded Coder and TI C2000. In this session, we'll cover three topics. We'll begin with an overview of the TI C2000 microcontrollers, followed by an overview of production code generation capabilities from MathWorks, and then a hands-on demo that shows three-phase motors simultaneously running with the new F28069M LaunchPad. So without further delay, I'm going to pass the control to Loretta Faluid from Texas Instruments, who's going to give us an overview of the C2000 microcontroller family.
Thank you. Hi, my name is Loretta, and today I'm going to be talking a little bit about the C2000 microcontrollers, which are built for real-time closed-loop control. Now, if you look at some of the applications where C2000 microcontrollers excel today, you will see things like renewable energy spikes. So these would be applications such as your solar power inverters, your wind inverters. You also see motor control applications. Then there are industrial drives, smart grid and PLC, transportation, and also digital power. These are all end equipment which C2000 microcontrollers are currently used today. If you look at the DNA of a C2000 microcontroller, there are three specific attributes which come together to make up the architecture of these solutions. We have the processing, actuation, and also sensing. In the processing attributes, there is a C28x CPU core, which enables single-cycle execution of math-specific control code. We also have a couple of accelerators which are on the microcontroller, which allows you to accelerate application-specific code. There's also a CLA real-time coprocessor, which enables independent multi-loop processing. Now, included in these MCUs are also the actuation piece. Now, the actuations are specific peripherals which enable things like high-resolution system control. So these could be like your high-resolution PWMs. We also have flexible system interfacing and also advanced system protection. The other attribute which I want to talk about is the sensing. Now, these will be specific to analog sensing. They're high resolution, high accuracy signal sampling. There's also high resolution digital signal interface. And also, we have asynchronous system monitoring and response. If you look at the portfolio of the C2000 microcontrollers, there are two distinct brands which you will always identify a device with. There's the Piccolo brand and also the Delfino brand. The Piccolo devices, or devices in the Piccolo family, are more of our low-cost entry line that feature a lot of the attributes which I talked about, but have really solid performance. These would range in performance from 40 MIPS all the way to 240 MIPS. The Delfino microcontrollers are our higher performance portfolio for higher performance types of applications. So these would be applications which would need performance from about 100 MIPS to 800 MIPS. Now, if you look in this picture, you'll see that there are three distinct microcontrollers which are sampling today. There's the F28070X, the F28037XS, and the F28037XD. The really cool thing about these three microcontrollers are that they're pin compatible and they're also software compatible. So this allows you to easily scale from a Piccolo, a low-cost platform, all the way to a really high-end platform or a really high-end application without changing your hardware or your software. Now, we also have the F28M3X microcontrollers, which are designed for industrial applications that require low latency, closed-loop control, plus host connectivity and system management. So if you look in this image, you will see that it includes the C28X processor along with the Cortex ARM processor. And basically, you have your actuation, your sensing peripherals, and also your communications peripherals. There are two distinct devices in these portfolios, and you'll see the performance ranges all the way from 60 MIPS for your control, and it ranges all the way up to 150 MIPS. For your host processor, so this would be your ARM Cortex MCU, you have 60 megahertz all the way to 125 megahertz. And like I mentioned, these also include your actuation and the sensing peripherals, which all C2000 devices include today. Now, we also have the InstaSPIN microcontrollers. These are C2000 microcontrollers with embedded InstaSPIN-Motion control software, and this software really enables you to identify, tune, and fully control any three-phase motor in minutes. We have InstaSPIN-FOC, and then there's also the InstaSPIN-Motion solution. The InstaSPIN-FOC includes the fast software, which eliminates the need for a physical sensor and removes manual tuning challenges. InstaSPIN-Motion builds on FOC and adds the spin-check technology, which enables accurate speed and position sensing using either the fast encoder or a rotor sensor. If you look at the MCUs, which include InstaSPIN today, you have three MCUs. So there's the F28069X, the F28069X, and the F28069X. And these will range in performance from 40 MIPS all the way to 180 MIPS of total system performance. The InstaSPIN MCUs also include the actuation and the sensing peripherals, so your PWMs, your ADCs, your comparators, and other great peripherals that are really needed for motor control. So now we've talked a lot about the microcontrollers. Now let's talk about how do you get started and what does C2000 provide. So we have Control Suite, which is our central repository of everything that you need to get started with software development. It is a complimentary download on TI.com, and in there you will find things such as applications, examples, libraries. You find device support information for some of our hardware kits and even for some of the MCUs. We have Code Composer Studio, which is our integrated development environment. This is supported it's supported all the way up from version 3.3 all the way up to version 5 and above. We also have hardware development kits, which I'll talk a little bit more on the next slide. And we also have many application-specific kits, which I'll also talk about on the next slide. And we also have many training and support opportunities for many people who want to learn more about our C2000 microcontrollers. And then we have third-party support, which, of course, we have MathWorks today to talk a little bit about some of their solutions for our C2000 microcontrollers. Now, if you look at some of the hardware development kits, we have our starter kits, which includes things such as our LaunchPad. Our Piccolo LaunchPads are our starter kits, which many people can use to get started on C2000 motor control types of applications without spending a lot of money on the actual kits. These kits start today from about $17. Then we have our control sticks, we have our peripheral explorer kits, and then we also have our prototyping kits, which are experimenter kits. So every single microcontroller platform, which you have seen today, has a prototyping kit or an experimenter kit, which allows you to go ahead and start doing some development and exploration on our solutions. We also have application-specific kits, which basically builds on our experimenters kits and provides application-specific examples for you to use. So we might have kits in the digital power applications. We also have kits for doing LED lighting. We also have kits for doing motor control. Now, the last slide I wanted to mention are our training and support. We have many workshops which are available to you to learn more about C2000 microcontrollers. We have application workshops, we have technical seminars, and we also have third-party training. We have online training which can be found on our website, and we also have our E2E forums which provides a community of engineers, factory engineers, and also external engineers to help answer some of the questions that you might have on getting started with C2000 microcontrollers. So with that, I will hand it off to Tom, who's going to talk a little bit about the MathWorks Embedded Coder solution.
Thank you, Loretta. So yes, I'd like to talk a bit about how you could use Simulink and embedded code generation to program the C2000 microcontrollers. But first, let me give an overview of this technique that is known as model-based design. With this approach, a model of your algorithm is the focus of development. You can execute the model as an executable specification by simulation. You can design using simulation, for example, convert floating point data to fixed point. You can generate code at any point in the process for prototyping or, as we will discuss, as part of the code that goes into your mass production device. Now, every step along the way, whether you're simulating or using test and verification tools, you can continuously test your algorithms as they move from executable specifications to your production code. Now, this technique of model-based design with production code generation has been used for a number of years now in many of the larger embedded controls industries, such as shown here with automotive, aerospace, and industrial automation examples. And the reason that they do so is because, as you can see, they realized significant development time savings, as you can read about in the user stories that accompany these images. The one example shown to the bottom right of the students are learning how to use model-based design is interesting. They haven't realized any savings because many students are growing up simply using models to begin with and not traditional paper specs and hand code. So they don't know what it's like to have used the old approach. Now, MATLAB is the foundation of MathWorks products. It's used by millions of people throughout the world for numerical analysis and visualization. Simulink is the block diagram modeling environment that includes the system dynamics as well as the algorithm. In other words, you would have the model of the motor interacting with the motor control algorithm, all within a Simulink block diagram interface. And Simulink is the foundation for what is referred to as model-based design. Now, MathWorks has several coders, C coders in particular. MATLAB Coder generates C code from the MATLAB environment I showed earlier. Typically, that's used for desktop deployment. Simulink Coder generates C code from Simulink, often with a real-time framework to do rapid prototyping or hardware-in-loop testing using something like Simulink real-time hardware. Lastly, Embedded Coder is the focus of this discussion because it's an add-on to the other code generation products and provides extra capabilities and optimizations for embedded systems. You can see, for example, it has processor optimized code. It allows processor-in-loop verification. It supports embedded target deployment, as we will hear later from Antonin. And lastly, it is the basis for our certification of functional safety standards, as shown at the bottom. Now, all of these coders, including Embedded Coder, by default will generate ANSI ISO-C, so the algorithm code is portable. And even though in some instances we do offer target optimizations. People often ask, well, how efficient is the generated code? What we have seen, even as long as 10 years ago in these published reports, is that if a customer works with the product and has good model guidelines, they can achieve code generated automatically that is generally on par with that of their hand code existing software in apples-to-apples comparisons. So let's talk a little bit about the model-based design process, starting with executable specifications. One would start by creating a model of their controller and their plant, their algorithm and their environment using Simulink. They'd have test inputs and they'd record the outputs. And they can determine if their algorithm is accurate and controls or interacts with their environment as using closed-loop simulation as shown here. Then with code generation, they can generate C code and run it in a real-time machine and connect that directly with their physical hardware. So instead of a plant model, they would just connect it directly to their environment, their hardware, perhaps on a test bench or in a prototyping environment. And this will show you if your algorithm can actually control the real system, not just using simulation. Lately, though, folks have decided that they can actually prototype directly on their embedded hardware, like a TI C2000 Microcontroller. And in this case, they can do the same type of prototyping environment, but determine if the code is actually practical, that it can actually fit on the resources provided by the embedded processor. So once you have done these these executable specification activities, you can now move to more of a detailed software design aspect just by reusing the same model. For example, perhaps your model used double precision and your embedded processor used single precision, or maybe you needed to go to fixed point math for an integer-only processor. Well, with the fixed point designer, you can automatically convert your floating point model to fixed point by answering questions as shown here, such as whether the ranges of your inputs and how much do you wish to protect for overflow and so forth. And there's a demo shown at the bottom that you could run to learn more about this tool. Also, one of the design activities is often to define the interfaces of your algorithm code. How do you want the algorithm to interact with your existing software framework? Does that matter to you? If it does, you have full control over the function call signature as shown with these options in user interface here. Also, in addition to defining your function interfaces or the entry points into your code, you may also want to define the data, how your data interfaces with calibration tools, for example. Would you like to use get, set, access methods as highlighted in this screenshot as a way to control how people would access the data in the generated algorithms? So by controlling the float and fixed point data types, function specifications, storage classes, and so forth, you have now created code that's ready for production generation. So let's look at this in more detail. The first thing you should decide is how do you want to deploy your algorithm, as shown in the model box here. You can generate code for the algorithm with well-defined interfaces using the function control characteristics I showed earlier, and then have a handwritten scheduler with device drivers interact with that algorithm just as you might have plugged hand code algorithms into your basic software framework. But sometimes people want more than just ANSI-C. In this case, it is possible to generate processor optimized code as shown here. You can see that the processor optimized code is part of what's generated by the tool, and it could include, for example, IQMath or ARM Cortex CMSIS optimizations. Then you want to know is how do you get the I/O? Now, in a lot of production organizations, the I/O is written by the software engineering team, and they've optimized the I/O and device drivers and scheduler for their particular software architecture. And so in that case, you would just get that from the software team. But in other cases, you may need all the I/O. Perhaps you have not written it, and you would like things like device driver blocks as part of your modeling environment. So when you push the code generation button, you would get the entire executable. So in this case, you may ask, well, where do I get the I/O for a specific device? For the C2000 family of microcontrollers, MathWorks has built-in support. You would simply go to your MATLAB window under add-ons, say Get Hardware Support Packages, and download the support for the Texas Instruments C2000 MCUs as shown here. When you install that package, you get a full suite of different I/O devices. You get a multitasking scheduler, and it's a fairly broad set of support. And you would look into this set of palettes to see exactly what devices are supported, what peripherals are supported, and use what's available. So now that you've created this system model with your I/O blocks and you are ready to generate production code for your complete system, the question is, are you ready to ship? Is there anything else that needs to be done? And in many cases, when you're using embedded control systems, there tends to be a higher degree of need to do formal verification. One way that we support formal verification is through the use of processor-in-the-loop testing. By this, we can refer back to that block diagram I showed earlier, and what will happen during a till test is you would hit the simulate button, and the algorithm would go from the Simulink model as generated code into your embedded processor, and as long as you've connected your embedded processor back to your host, perhaps using a serial device, you can automatically, during the simulation, download the test cases from the Simulink model, run them on your embedded hardware for a single loop, and then bring the outputs back from your embedded algorithm to Simulink for interaction with your closed-loop plant model. This is a non-real-time synchronous co-simulation environment, but it's very useful to show that the results that you get on the target embedded hardware match the results you get with your simulation environment. You can also get profiling information to determine how fast the code executed within the algorithm to find the hot spots in your algorithms and optimize even further. So processor-in-the-loop testing is a nice feature of model-based design. And it is also a key point in leveraging certification support provided by the MathWorks for these industry standards. We have a certification kit product which supports the standards you see here, including the automotive, industrial automation, rail, and process control industries. You can see Embedded Coder is one of the supported products for the standards, and they all have certificates from the TÜV-SÜD indicating their suitability for use in these standards. But as you study the certificates in this kit, you'll realize that it is required in order to obtain certification to do things like processor-in-the-loop testing to make sure your code on the target gives you the same results as in the model. And with that, I'll just turn it over now to Anton and Ansel, who'll go another level deeper and talk about our support for the C2000 family and do a nice demo illustrating the use of our products. Thank you.
Thank you, Tom. So I'll be playing a video that shows how to create a Simulink model to control two motors with the F28069 LaunchPad. But before I do that, I just want to give you an overview of what is supported with the Embedded Coder support package for TI C2000 devices. So first, here is the list of supported devices. So we support the Piccolo family of devices, and that includes the O2X, 3X, 5X, 6X. The F28069X is in progress. We support the Delfino family of processors, and that's the F28033X family with the popular F28335 and its FPU. We also support the non-FPU version of that device, that's the F28332X variant. We are in progress of supporting the F28037X device. We also support the fixed point variants, which are a bit older, the F280X family and 281X family. We also have support for the Concerto, which is a dual-core C28X plus Cortex M3, and we target both the C20X side, C28X side, and the Cortex M3 side, and that is supported from our R2014B release. So our support includes a scheduler, like Tom said, and that offers you the opportunity to schedule periodic tasks, and we do that using the CPU timer 0 provided by the C28X. You have the ability to schedule interrupts, trigger them from peripherals, and react on them. You can also decide to trigger an interrupt via software. We offer the capability of scheduling idle tasks that will run in the background, and we have a bunch of advanced concepts like the ability to replace the base rate interrupt of the rate monotonic scheduler with, for example, an ADC interrupt if you want to have your scheduler running from an ADC interrupt. We also have the capability to trigger ADC conversions from PWM. You can also offload your main CPU by running code on the CLA for some of the Piccolo devices that have that control law accelerator. We have the ability to load code in Flash but run in RAM. That offers performance improvement, especially on devices like the F28335, where the Flash is actually slower than the RAM. You can also offload your CPU with mem copies by using DMA, and that all takes advantage of our preemptive rate monotonic scheduler. So that offers multitasking where your fast rates are actually preempting your slow rates, and that's built in Simulink rates. So here is a list of supported peripherals, and we have very flexible support for these peripherals. So that includes ADC, analog I/O, analog comparator. We have support for GPIOs, QEP, PWMs, the capture modules, CAN, I2C, SCI, SPI, LIN, Watchdog, DMA, and like I said, we try to go deep into flexible functionalities for these peripherals where you can set your acquisition window for ADC, trigger ADC events from PWM, and raise interrupts on various events that these peripherals may trigger. For example, we have examples on how to use the QEP module to react on an optical encoder to do your motor control positioning. We use the ECAP modules with our motor control examples to react on Hall sensors and do motor control positioning. We also have examples on how to use a sliding mode observer to do sensorless motor control. We have support for a lot of TI motor control kits, especially the ones based on the LaunchPad. So we have a file exchange submission with a video for both the F28027 LaunchPad and the F28069 LaunchPad. The first one is controlling one motor with the DRV8301 booster pack, and the second one is controlling two motors with two of these booster packs. We also have support for the popular DRV8312, that's a shipping example of our support package. We also support an older platform which is based on Spectrum Digital DM 550 plus the Easy DSP, and that's also a shipping example as part of our embedded coder support package for TI C2000 devices. We also have support for the high voltage motor control kit. Just send us an email and we'll give you Simulink models. And now I will play a video that will show you how to control two motors with the F28069 LaunchPad.
I will present today how to control two three-phase brushless motors using one F28069 LaunchPad. There is a prerequisite to better understand this example. I strongly recommend you watch the video entitled Simulink Motor Control with TI LaunchPad. This previous video is controlling one motor with a F28027 LaunchPad. I strongly recommend you go through this video as it will explain how to install the support packages needed for this particular example. So here is the list of hardware required for this demo. You need an F28069 LaunchPad. You need two BoostXL DRV8301 booster packs. Note that the F28069 LaunchPad can take two booster packs at the same time, and these are the inverters, so we're going to use one for each motor. And you need, of course, two PMSM three-phase motors. There is a packaged mini dyno kit that you can get from TI. This is the product code 2MTR-dyno, or you can use any two PMSM motors that may be shipping with other kits. So here is what I have on my table. This is my F28069 LaunchPad. You can see the two slots for the two booster packs. This is my first booster pack, which is connected here to this motor. There are a lot of cables here. These are my QEP and Hall sensor cables. They're not connected today because I'm running sensorless. The Hall sensors and QEP cable for the second motor, and you can see that the second motor is connected to the second booster pack. So I'm going to connect both of them to the F28069 LaunchPad. There is no dump-proof connector, so make sure that you connect them correctly. I have a power supply here. It's just a laptop power supply that's not connected right now. That's going to give me 20 volts, and I have shared that power supply across the two booster packs. I also have my 5 volt USB cable that I can connect to my computer, which will power the F28069 LaunchPad. And installation functions that are good to remember: target installer to install new support packages, target updater to make sure that the third-party tools are correctly installed, and check env setup. And in this case, it's good to run it against CCS v5 or v6. F28069 check. That's probably the configuration that will be useful today. So let me go to the Simulink model. So here is what I use to control the two motors. I'm just going to generate code and run it, and then I will go through explanations on how I got there. So I can press that build button. It will generate code for this model. It will invoke the CCS compiler, and it will load the code on the F28069 LaunchPad that I have connected right now to my USB cable. I haven't connected high power yet. Let's wait until we load the code, then we can start the 20 volt to spin the motors. You can click on the view diagnostic to follow the build steps. You can see the generated code being compiled. Here we call a scripting tool provided by CCS to load the code onto the target. My debug session is starting. I'm connected to my target, and my code is loaded on my target. It's a little hard to see, but I have an LED blinking. Yeah, you can see it here. It's a blue LED blinking, just to see that the code is running properly. Alright, so the code is flashed on the target. So what I'm going to do is I'm going to disconnect my USB cable. So now nothing's powered. I'm going to connect my high voltage, it's only 20 volts, but this should spin the motors now. It should boot the code and provide high power at the same time. And now you can see that both motors are spinning on my dyno. You can notice I haven't connected the two motors together. They're just freely spinning right now for the sake of the example. Of course, one thing you can do in the future is connect these two and have one drive the other, and have one motor act as a load while the other would be the motor on the test. So how did I get there? So here is my Simulink model. One thing very important, always enable colors in your model, and if you look at the sample time legend, we have multiple colors here. We have this red RAID group, which is running at 50 micro. We have one interrupt, which is asynchronous, and I can tell you it's running also at 50 micro. So I'm running these two motors at a 20 kilohertz rate. I have a speed control loop every 10 milli, so every 10 milli I'm going to refresh my torque demand to both of these torque control loops for each motor. And I have my LED blink at 0.5, so I'm toggling the LED every 0.5, which gives me a blinking period of 1 second. So there are a few modeling concepts that I would like to show with this demo. So the first one is the target selection. Make sure you've selected the right target. The F28069 LaunchPad comes with an F28069M, and the M is very important in that case. It doesn't have the same memory map as the other F28069, so you need to select the C2000M.cmd file. It's not the same linker command file as the regular F28069. The devices are similar, but the IQMath tables are located at a different memory location for the M device, so it's very important that you select that M device, which is provided out of the box. Just press the browse button and you have all of them provided here: the plain 069, the 69F, and the 69M. Second modeling concept that I would like to demonstrate is the PWM synchronization. So I have two motors, and the first motor is going to be controlled by this side of the model, while the second motor is going to be controlled by this side of the model. The two PWMs have to be synchronized. What I do for that is I'm using PWM 1, 2, 3 for the first motor, and they're triggering ADC A0 and B0, which are sensing my IA and IB for the first motor. I am using PWM 456 for the second motor, and they're triggering ADC A3 and B3. So now, like I demonstrated before, the PWMs are synchronized. So the first three, 1, 2, and 3, are synchronized together, and the counters are just in sync with each other. The way I ensure this is by sending a synchronization pulse between PWM 1, 2, and 3. The way you do this is you set here synchronization output, and I'm going to send the pulse when the counter equals 0. Okay? So this will send the pulse to PWM 2. Now you can see on this first one I'm not reacting on any pulse. Synchronization action is disabled. This is the initiator of the pulse, so it's my reference for the synchronization. Now if I go to PWM 2, when counter of PWM 1 equals 0, it will send the synchronization pulse. PWM 2 reacts on it by setting its own counter to 0. In that respect, both of them are synchronized. They're all going to be set to 0 at the same time. PWM 2 also outputs a synchronization pulse to PWM 3, and in that case it's just a pass-through. We don't want to do anything. PWM 1 is eventually going to reach PWM 3 via PWM 2 with a pass-through here. On PWM 3, same as PWM 2, I'm going to react on the synchronization pulse by setting a counter phase value to 0. Oh, one thing I forgot to mention, once you set this to 0, it has to count up after sync, because it's counting mode is up and down, so when you reach 0, obviously after that you want to count up. This is important. This also has to be set on PWM 2. Now, what PWM 3 does, in the previous video with the F28027 LaunchPad, it was just disabling the output because nothing was there after that. Now I have a second motor to synchronize, so here I am passing the synchronization output pulse, and this will reach PWM4. So now let's look at what we do with PWM4. PWM4 is for the second motor, and now what I'm going to do is I'm going to synchronize the counter of PWM4 to the counter period instead of synchronizing it to 0. And when PWM1 to 3 are reaching 0, PWM4 is reaching the counter period. And you will see that I'm going to do the same with 5 and 6. So 4, 5, 6 are going to be set to the period, while 1, 2, 3 are going to be set to 0. So in that respect, they're dephased by 180 degrees. Same deal, I'm passing the synchronization output pulse as a pass-through, so that will reach PWM5, and PWM5 is going to be the same as PWM4, setting the periods when you reach the pulse. And you can notice here the countdown after sync. When we reach the period, we want to count down. And the same, I'm passing the synchronization output. PWM6 is going to be the same, with the little difference that there's nobody after that, so the synchronization output reaches finally a dead end and it's now disabled. So here is a picture that summarizes what's happening in this model. We have our PWM sync triggering when the PWM1 counter reaches 0, and that synchronizes the counters of PWM1, 2, and 3. That PWM sync will also synchronize PWM 4, 5, 6. When PWM1 is 0, PWM 4, 5, 6 will be set to the counter period and will count down after the synchronization. You can see the ADC triggers happening on the periods of PWM 1, 2, 3, as well as the periods of PWM 4, 5, 6. The ADC trigger of PWM 1, 2, 3 will trigger ADC A0, B0. At the end of the ADC conversion, an interrupt is generated, and that will trigger the field-oriented control algorithm for motor 1. When PWM 4, 5, 6 reaches the period, ADC trigger number 2 is happening, and this will trigger ADC A3 and B3. At the end of the conversion, an interrupt is generated, and that will trigger the field-oriented control algorithm for motor number 2. You can notice that full PWM period is set to 20 kilohertz or 50 microseconds, so that gives us about 25 microsecond maximum for the ADC conversion and the field-oriented control algorithm for each motor. So you can notice that our code is running pretty efficiently, as it has to complete within that 25 microsecond and leave enough time for the lowest priority tasks to execute. The last modeling concept I wanted to talk about is the ability to trigger the Simulink scheduler based on an ADC interrupt. If I go back to my model, you may have noticed that I only have one interrupt that's triggering the FOC algorithm for motor number 2. I could create the same model with two interrupts, one for motor 1, one for motor 2. The problem when we use interrupt is you get that purple color, and Simulink loses the ability to know that this is a periodic interrupt which is associated with a fixed sample time. We can fix it for at least one interrupt. If I go to my config set, I have the ability to tell Simulink to trigger the scheduler based on the ADC interrupt instead of the standard timer 0. By default, the scheduler interrupt source is set to timer 0. When we do this, we book CPU timer 0, we set the periodicity of timer 0 to the base rate of the Simulink model, and that triggers an interrupt at a fixed interval. That's the red color in my model. Here I have the ability to say, I have set my ADC interrupt to a specific rate. Now please, Simulink, use that interrupt to schedule the entire scheduler instead of timer 0. And that's what we do here. That offers the ability to keep a known sample time and use blocks that would need that sample time. I'm thinking of blocks like the buffer block, like PID blocks, or any block that would need an input sample time. I hope this gives you a good base to start playing with this dual motor control setup. For the future, as enhancements or things you can try to implement a sensor-based motor control algorithm using either Halls or QEP. To do this, you can type on your MATLAB prompt. There is a standard demo. If you type C200069 PMSM-FOC, that will help you implement Hall sensor-based position sensing. There are other shipping demos like the C2808 PMSM-FOC. This one will show you how to use a QEP to get the position of the motor. There are also demos that will show you how to use the CLA. So we can put the FOC algorithm on the CLA and therefore save a lot of CPU time to do some lower priority tasks. The CLA would require a conversion of the algorithm to floating point. There is a shipping demo that will show you how to use the CLA. If you type C28069, just tab it, and you have C28069 PMSM-FOC CLA that will show you how to use the CLA. And this CLA demo is also using Hall sensors as a position technique. You could also do parameter tuning and data logging via external mode. There is a CAN connector on the F28069 LaunchPad. You can go through our external mode based on CAN demos to start logging data and tune parameters like PID gains while the motors are spinning. You can type C28x_CCP, and that is a good starting point for external mode based on CAN. Another good avenue to pursue would be to connect the two motors physically together and start having one acting as a load while you actively test the first motor. I hope this helps, and I hope this gives you a lot of ideas to try. Thanks for watching.